What I know is, what did I ask? Okay. Oh, how would you classify this kind of a relationship?
It is. Oh, you are looking for the word. Well, it's linear. And
It is. I like that. So it's linear. What else?
It's a direct personality.
Is it or not?
Yeah.
What we talked about on Thursday was they here. All of these were direct relationships. All of these were a direct relationship, but only one is it has to be linear and go through 0, 0 before you can call it a direct proportionality. And so I would call it linear. I like that. And it is a direct relationship, but it's not a direct proportionality. Now, another way you could tell that is if it were a direct proportionality, let's try one. Let's go from 10 to 70. And I'm just estimating here. If you made this one 7 times bigger, if it was really a direct proportionality, then this would get 7 times bigger. So how many times bigger? Is that you get 7 times bigger? Okay, that doesn't seem right there, okay? Even this one, that gets about 2 times bigger. This gets about, yeah. So you see that it's not really a direct proportionality. You okay on that? All right, so let's move on. Now, this is where we've actually spent time with the direct proportionality. We just haven't done direct relationships. Let me go ahead and I'll read just a little bit here, and then I'm going to get into, this is the part I really like teaching. We've actually had a little bit on the inverse proportionality already. When I want you, as I read this, I want you to highlight what you think is an important part of this paragraph. When analyzing quantitative data, one is often interested in discovering an exact mathematical expression that shows how one quantity varies with another, while all other quantities are held constant. There are several ways of discovering what this relationship is, if it exists. One of the most useful methods is the graphic interpretation of data. To get an idea of how this method is applied, we will investigate a few of the more common relationships. Fortunately, many physical quantities are related in one of 6 ways. As a matter of fact, of these 6, I would say the first 4 are found the most in physics, engineering, okay, and we will study all 6, but these are more major and these are a little bit more minor. And so another thing is, just like people don't want to say deoxyribonucleic acid over and over and over, they say DNA. Okay, so what we're going to do here is a direct proportionality. If I want to write it, I'm going to use a little abbreviation called DP. That's direct proportionality. Let's do another one. Let's go down to this one. Direct square proportionality. Okay, I'm going to use little abbreviations for that. Let's do another one. Direct.
Square mean?
What now?
What is direct proportionality? Does that mean it's
I'm just making an abbreviation for this one right here.
But is that like an exponential graph?
Yeah, this would be a abbreviation for directly proportional to the square. It's called a direct square proportionality. And this one is a direct square root proportionality. Okay, now let's go to inverse. Inverse proportionality, inverse square proportionality, and inverse square root proportionality. Here we go. That'll make it a little easier on everybody if we use abbreviations. Got it? Okay, so now we've got to find out what this means. Are you okay on this paragraph? Everybody know what quantitative data is? Don't shake your head if you don't. Everybody know what quantitative means? Numbers, right? Quantity is number producing. Okay, let's go to the next paragraph. In considering each of these relationships, if actual experimental data were used, there might be considerable scattering of the plotted points due to the experimental error in the data. Although this would be realistic, it would obscure the underlying relationship between the variables. Hence, the common relationships are illustrated with idealized data. Therefore, there is no experimental error in the data, which are not real data in the usual sense. Whew. What do you think about that paragraph on Monday morning? Huh? Okay, let's analyze that a little bit. they could use real data from a real experiment. And just like you did on that temperature graph, if they did, you would have to worry about where to draw the best fit line, and it might obscure what they're really trying to teach. What they're really trying to teach is what is the mathematical relationship that exists. You get it? So what kind of data are they going to use? Near, and there's a couple that are rounded off, so I'm going to say perfect or near perfect. Who said that? That was good. That's right. So they're going to use perfect to near perfect data. So you'll see me do a couple things with this that you normally wouldn't do in a lab, because I know the lab has real data and it has error. The good news for you, though, on ACT tests or SAT tests, they want to use almost perfect data. You know why? Because if somebody misses the question and the data has error like that, they could say, well, it had too much error. I didn't, So even on those kind of tests, they're going to stay away from real data and be more likely to use near perfect data. You got that? So, all right, well, here we go. We already know about direct proportionalities, right? And we know about direct relationships and direct proportionalities. Let's go to inverse. How is the length in centimeters related to the width of centimeters of any rectangle of 60 square centimeter area? Now, I used to, and I just I could have done that. I used to do that as a homework assignment. Go home, get a piece of graph paper. Now make me 10 rectangles that have an area of 60 square centimeter. And what do you think would happen if I said, go make me 10 different rectangles that have different lengths and widths, but they all have to have an area of 60? What kind of numbers do you think would come in? What do you think? So let's take a look over here. And here's my data table. It probably would have come up something like this. Hey, I had a length of 60, so the width was 1. Length of 30. Okay, you see that? Now, what I'm going to do is, you guys are very smart, and I have to be careful, and I don't want to get into one of your traps of saying, well, you could have thought about it this way. So what I'd like to do is let me teach the lesson one way, and then we can talk about the could have later, okay? What I want to do here, when I want to analyze a data table, especially one that has near perfect data, I'd like to find the independent variable first. So what I'd like to ask you to do is, which one of these do you think was the independent variable? Which one did the experimenter say, I chose those? I chose this one, and then the other one responded to that. Which one? If you had to guess. Yes?
Length.
Why do you say that?
I guess it's on the left.
Okay, now, unfortunately, when I was trying to teach that to you earlier with scientific graphing, math will always do that. Math will always put X on the left and Y on the right. You see that? And yet, that doesn't mean that a data table you see is going to be like that at all. So look at it again. Look at the data again. Is there any other clue that tells you, what do you think, Rollins? This one, truly, and then I think a human manipulated this. A human wanted to have 1, 2, 3, 4. You see that? I don't think a human chose 6.6. So I think in this case, I'm going to start with this as my independent variable. Now, the reason I ask you to do that is that this whole packet, I would like to see the relationships as if we always see it through the eyes of the independent variable. Yes?
What's the purpose of putting the independent one on the right?
I don't know if there's a purpose. If you did an experiment and you made a data table, maybe you would put your independent variable on the right. Is that okay? What you probably don't like is that if math always puts X on the left and Y on the right, then why are the scientists messing things up when sometimes they don't? And that is part of the experiment. When you do take the ACT and there's a data table there, they don't always put the independent variable on the left. But if you read the experiment, you'll say, I know what they did. That was independent variable, and that's the responding variable. So there's nothing that says they have to put it on the left and right like they do X and Y for math. Okay, I'm not trying to make your life hard. I'm just saying nobody says it has to be one way or the other. But in this case, I have this clue, and I also have this clue. Unless there was a reason not to. the independent variable should be on the x-axis. Okay, so width is the independent variable. So now what I'm going to do is I want to analyze the data. Does everybody have a calculator with them? Okay, you'll need a calculator. Now, I'm going to try to show you this. We probably will, I'm hoping to get to maybe three different relationships today. We'll see if we can. Well, first of all, as I look at the data table, I notice that as width gets bigger, then what happens to length? As width gets bigger, then what happens to length? And it gets smaller, doesn't it? Now that is a clue that it's one of the inverse relationships. Another word they use is indirect, same thing. It's one of the indirect or inverse relationships. If you get it higher, the dependent gets lower. That's all we know so far. Now we know from here, there are three of these that we are going to study, three that are inverse. Which one is it? So which one is it? So what I'm going to do is, I'm going to do this thing that you normally wouldn't do on real data because your data might have too much error. But I'm going to do it on idealized data to show you how this works. I'm going to go here and I'm going to make my independent variable go from 1 to 4. That's what I'm going to do. And in the world of ratios, I just made it 4 times bigger. Okay, so imagine that my independent variable, what would happen if I made that 4 times bigger? Well, let's go over here. The original number was 60, and it's going to go to 15. So in the world of ratios, what's 60 over 15? What's that give you? Everybody. 4 times what? Smaller. Now I'm going to do it again just to make sure that I don't get fooled here. Let's go from 1 all the way down to 9. Let's try that one. Let's go from 1 to 9. If I make my independent variable go from 1 to 9, I just made it 9 times bigger. So why don't you tell me what happened here? What happened to the dependent variable? How many? 9 times smaller. So if it's truly an inverse proportionality, as long as I don't have too much error in my data, I could play the numbers game on a data table. And that's what they do on these tests. Some of these SAT and ACT tests, they'll give you a data table, and if you know who's independent and dependent, you can very quickly figure out what it was, if you just know how to do this little pattern here. All right. What kind of a graph will you get if it's an inverse proportionality? And by the way, the inverse proportionality is the only one where if this gets 4 times bigger, you get 4 times smaller, 9 times bigger, 9 times smaller. What if it went the other way around? What if it got 9 times smaller? What if the independent variable got 9 times smaller? What would happen to the dependent? 9 times bigger. It'd be on the inverse, wouldn't it? Now, if you look at it here, here's a data, again, this is idealized data, but when I do end up testing you, I will have like one whole page of data tables. The whole thing, you're going to see a bunch of data tables, and I'm going to ask you about 15 questions about which data table is an inverse proportionality. And I'll say, which data table is a direct square proportionality? So eventually you'll be able to do that. And then I have another page where all you see is graphs. And you had to tell me which one it is. Yes?
Is that an inverse proportionality to the square?
Is what now?
Is that an inverse proportionality to the square?
This one or this one?
Both.
They are. As a matter of fact, this graph came from this data table. So they're both inverse proportionalities. Now, how do I know if I don't actually have, I didn't answer your question, did I? I looked at your eyes. Do it again, one more time.
I was saying, is it an inverse proportionality to the square?
No, not this one.
Why not?
Okay, now, good news for you, good and bad news, good and bad news. All the direct relationships have their own individual looking graph. And you can actually kind of look at them and tell. But all the inverses have curves like this. So how do you know which inverse it is? Okay, so now we figured out how to do it with the data table. And again, you have to be careful about doing this on real data. If you have too much error, you can be off pretty much. And it's okay. In the real world, when you do your experiments, you might say 4 times bigger, 3.8 times smaller. It's probably pretty close. That's probably it, you know? Let's go down here, and I'll show you another way to do it. But now, how do we do this here? Well, what I do is, if I'm careful enough, I can actually do x1, 60. I can actually give myself a couple data points. How about this one? Ooh, I see it, look. 4, I don't know, 15, something like that. Now, let's play the numbers game on the graph. Let's take a look. Which one do you start with again? Which variable? The independent variable, which is x, isn't it? So watch. What happened to my x variable? If I went from 1 to 4, what happened to it? 4 times bigger. Now, what happened? How did the dependent variable respond to that? If you make this 4 times bigger, what happened to this guy? And you put this in your calculator, 60 divided by 15 is what? Oh, see? That gives you more evidence that it's an inverse proportionality. Okay, now, we will eventually get to inverse square. Get that? Have you guys studied that already? You already knew what inverse square was? How did you know about inverse square? Just because that one time I mentioned it?
Yeah.
Oh, okay, we'll get there. We'll get there. Now, is everybody okay on that? Again, you guys are very, you're a little bit higher level than a lot of students in your class in that you can see ratios very quickly. And so this shouldn't be too hard for you. But now I'd like to tell you, how does a scientist actually prove that it's an inverse proportionality? They probably won't be playing the numbers game because there might be too much error. And they also probably won't play the numbers game on the graph. You think you know?
Yeah,
Okay,
they could graph and do a simulation of 100 times and find the error in statistics.
they could do that. As a matter of fact, let's try this. If these are, all right, here's my question mark. If length and width are inversely proportional, how do I draw the equation? So here's my question mark. If it is an inverse proportionality, what do I think the equation is going to be? I know it's Monday morning. Karen, I'll bet you know. You're looking right at me. Karen, how would I write this equation if it is an inverse proportionality?
You would put length and width on the same side.
Yes. Now, so the good news is we're going to try to prove that they're inversely proportional, but you know what else I need? I need a constant. And you know what? In all the other cases to find the constant, I found the slope of a line, didn't I? You can't do that here. Why can't I do that? Let's see who's smart. Why can't I find the slope of this line?
It's not linear.
What now? Okay, but can you find the slope of this line?
It's like simple.
So how many slopes does a straight line have? How many slopes does a straight line have? 1. How many slopes does this have? Infinite. There's a slope here, there's a slope here, there's here, and here, and here, and here. You can't find the slope of a straight line, of a curved line. It has too many. But I want to find this. I need to find that constant to finish my thing. So I'm going to show you how scientists actually do it. Let's turn the page. All right, now watch. This data table should look very familiar to you. It's the same one that was on the last page, except they added a column. Now, when you eventually make the transition from a hand-drawn graph to using the computer program, here, one of the options will say, new calculated column. So you'll have your data, okay? Let's say you have your graph. Let's remind you what the graph looked like. You said, I wonder if that's an inverse proportionality. I wonder what it is, and I wonder how I can find a constant. And what you would do is tell the computer, right now you're going to do it by hand, you're going to tell the computer, I want to make a new calculated column. Oh yeah? What do you want to do? I want the inverse. I want the reciprocal of the independent variable. So here's my length, here's my width, and here's my 1 over width. Everybody see that? Now stay with me. I know it's Monday, but you're pretty good at this. And look what happens. Notice how the graph changed? I'm graphing length and not width, but what? This is 1 over width, isn't it? You say, why would you do that? Why would you do that? So watch what I'm doing here. This graph proves that, watch now, this graph proves that L is directly proportional to what? No? The inverse of width. If you multiply it times some constant, right? Now stay with me, look at this. If you can prove that L is directly proportional to 1 over W, let's rearrange that. Rearrange that equation, what do you get? Multiply both sides by W, what do you get? Ding, 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 ding. And this is the way a scientist does it. They normally wouldn't play the numbers game. I want you to learn how to play the numbers game so you can kind of get an idea how it works. But here's the way they would do it. They would make a secondary graph. And the secondary graph, if you can prove that L is directly proportional to the inverse of W, then you can prove that L and W were inversely proportional to each other. Is that too much for this morning? And guess what I can do with this line? What can I do with this line? Say it. Find the, say it. Slope. And guess what the slope's going to be? Say it. Starts with a C, but the symbol is K. Find a constant. Okay, so anyway, what we're going to do here is you now can not only prove that L and W are inversely proportional, you can actually find the K. And so the slope is going to be K. Wow. And let's see who's really awake today. What is the slope of this line going to come out to be? Raise your hand. Raise your hand. Wait a minute. Wait a minute. I don't have it. Sometimes I don't have any money. No, you're out of luck. Okay. All I have is a 5. Sorry. I'll give him a 5 for that. What's the slope going to be? Anybody, raise your hand. Show off. Oh. These are the smartest juniors in school. What is it? No. What's the slope of this line going to be? Anybody? Oh no, I can't believe it. Not the entire class. Yes, you should. How much? What is it? Wow, okay, that's all right. That's all right. Nobody? No? That's another thing. You guys have to remember, you have a certain amount of being mathized. All right? Just like a while ago, you just can't handle it that the independent variable is on the left. On the right. All right, another chance. Yes.
5.
No.
K.
What?
K.
Well, okay, it is constant, but what is that number?
Is it 6?
7.
It's 6.
What?
Is it 6?
6? No.
Dang it.
You left something out here. You left something out right there.
It's
See, you forgot the original experiment. Yes.
60.
Yes. 60. The original experiment is to generate data. They said, give me about 10 rectangles that all had something in common. What was it? That their area was what? 60 square centimeters. Now, if you remember in the book, of course, what does it say? The length times the width equals what? Area. And what was it that was constant in this experiment? Not length, not width, but area. So anyway, some neat things for you. Number one, how do you prove that an experiment you do is really an inverse proportionality? You do a secondary graph between this is still the dependent variable, get that? That's on the y-axis, but instead of W, you do 1 over W. And if you can prove that L is directly proportional to 1 over W, the inverse, then you prove that L and W are inversely proportional to each other. Yes?
Is the slope though not the independent variable divided by the independent variable? Why are you multiplying? I know you're trying to find 60 is the problem, but how is that?
Okay, because this right here is y equals mx. Y equals mx, and x is 1 over W here. So I put y equals mx, and I proved that this was directly proportional to the inverse of w. So now if I multiply both sides by w, you get LW equals k. And in this case, the slope of that line is going to be 60. Matter of fact, it'll be 60 square centimeters. All right, what do you think? I got to look at half your faces, so I get to look at half your faces to figure out what's going on. All right, what I'd like to do is, you don't have to get super close to your partner, but I'd like you to go to the next relationship and do what I did. Figure out who the independent variable is, figure out is it direct or inverse, and then play the numbers game on the data table, play the numbers game on this, and then if you need to do a secondary graph, figure out what the secondary graph is going to be, and then don't turn the paper over yet. After you think you've figured out the secondary graph, it's going to be showing up right here. All right, sit with somebody, go sit with somebody, and it's taking about 5 minutes to figure out what it is. Yes?
Is it possible to have a direct proportionality? Is it negative?
Okay. A direct proportionality that doesn't go through 0, 0. I'm not saying it can't be direct, but it won't be a direct proportionality. I'm trying to think if I could generate data in my head. You can get a negative slope, and it could be a linear, and it could be a direct relationship, meaning as I got bigger, you got smaller, but it won't be a direct proportionality.
If you use negative numbers, though, could you do it?
Well, negative numbers. Now, if I had a graph in this quadrant right here, let's see, how can I make a negative slope?
No, I mean, like the graph of y equals negative x.
Oh, y equals negative x? Okay. So let's say x is 1. So negative 1, x is 1, y, no. If x is 1, y is negative 1. X is 2. Okay, now, the only way I could call that direct proportionality is if I negify everything. I'd have to think about that. That's a good question. Man, that's a good question. It does go through 0, 0. You're in the fourth quadrant, aren't you? I'd have to try that. Okay, maybe mess. Wait, why don't you mess with that? No one's ever asked me that, ever. And yours actually does go through 0, 0. It's just got negative. Wow, interesting. I don't know if I could do it. See, in science, you wouldn't have an experiment that would have negative unless you had some kind of scale that had negative numbers. Yeah, unfortunately. Yeah. All right, now you're gonna find out which one is the independent variable, which one's the dependent variable. Then you want to try to play a numbers game. Is it direct or indirect? Play the numbers game on the data table. Play the numbers game on the graph, and then see if you can figure out how would a scientist prove that it really is that what you say it is? Everybody talk, okay? You guys, you have, on Density Detective, you haven't finished it. And so, I don't know when you can show up, but you need it sometime in the next 2 days or so, maybe by Wednesday. You need to come in and finish what wasn't finished. Now, the good news, I know it's busy work, but what you don't have written in your book that they have written in their book, you can use it, but you have to actually finish it. And then you'll get the grade they got. Okay. But right now you don't have a grade. So today, if you want to, I'll be here after school also. And lunch today is fine. Tomorrow morning, lunch tomorrow.
I think I'll be in at lunch today.
Yeah. All right, is it working? Is it working? What do you think? Maggie, is it working?
It's what Mike was asking.
All right, everybody stop and go back to your seats, and let's see how well you did, all right? Let's see how well you did here. All right, ready? Now, to me, the reason I think this is a very, very powerful thinking tool is that even though we're only going to do 6 relationships here, and I could go to electronics or economics, or I could do physics or chemistry or biology, and I can use this tool to help me analyze the data. And that's why this is a very, very powerful tool, okay? I'm hoping you understand. I'm not just going through the motions here. This says here, how is the area of a circle related to its radius? And it says, this figure shows area plotted against radius. So which one did you think, let's see what I'm calling. Which one do you think was the independent variable? And, all right, Nathan. And what made you say that? Yeah, but I thought in math it was on the left side. The X was on the left side. Okay, so if you had to say, I might scramble these up on a test and you say, well, that's not fair. Just put it on the right. What do you think?
There's no good reason for the area to be on the y-axis, so I thought it made sense to have the radius in centimeters on the x-axis, and also it went up by 0.5, which is really easy to read.
This looks very human, doesn't it? This is very human manipulated. And so this is the independent variable. Now, another clue would be down here. Radius is on the x-axis. You get that? All right, so that's step number 1. Find out who the independent variable was. Now, I don't know if you knew this, but you can't play the numbers game. You can't enter the world of ratios by using 0. Does everybody get that? I hope you didn't say, well, let's go from 0 to 1. That's how many times bigger? That won't work. That doesn't work. 0 doesn't work in the world of ratios. Now, but I might go from 0.5 to, I don't know, how about 2.5? Let's try that. I just got 5 times what? As this got bigger, this got bigger. As radius got bigger, area got bigger. It must be one of the directs, isn't it? Isn't that one of the directs? Which one? Well, when this got 5 times bigger, this area got, ooh, what's that? Did you put that in the calculator? What do you get? If you didn't have the calculator out, you're just kind of guessing. What do you think? How many times?
24.5.
Okay, 24 point what?
5.
Okay, and again, some of these are rounded off, so even though they say it's near perfect data, near perfect, well, I don't know what that could be. Okay, let's do another one. Let's go from, why don't we go from 1 to 4? Let's go from 1 to 4. That got 4 times bigger. And what happened over here? It went from 3.1. Wow, what's that? If you go from 3.1 to 50.2, how many times larger is that? Put that in the calculator. No? Ryan, what'd you get?
No, I don't have a calculator.
Uh-oh. Okay, you're going to need it, okay? You're going to need it. All right, what's everybody got? 50.2 divided by 3.1.
16.
How much?
16.
15 even?
16.
Oh, 16. I don't know what this is. The independent got 5 times bigger, and you got 25 times bigger, and then you got 4 times bigger, and you got 16 times bigger. I don't know what this is. Yes, I do. Yes, I do. Whatever you do to the independent variable, the square of that will happen to the dependent variable. Oh, and this is a very famous called direct square proportionality. Yes? Now, you're going to tell me it's a direct square proportionality, question mark, prove it to me. Now, this is what scientists would use. They would use this word. What I did on the last graph, I'm going to do the same thing here. We need to straighten out the curve. How do we straighten out the curve without looking on the next page? What do you think? What now? log. I don't know, I'm not saying I couldn't, actually it's easier than that. But what would my secondary graph be? Okay, let's try it. What you're trying to tell me is, you're trying to tell me that area is directly proportional to not radius, but what? Squared, isn't it? Let's try it. What if the radius was 1? Let's say this is 1, just pretend. Let's pretend that's 1. 1 squared was 1. Data. But what if I made this 5 times bigger? And this 5 squared would be what? 25. And so look at what happened. I made this 5 times bigger. This got... So here's what you're trying to prove. Prove to me that A is directly proportional to what? Uh-oh. Can't lose you here. To do a secondary graph, prove to me that A is directly proportional to what? Not square root. Let's look at it. The square of R. Okay, let's flip it over. And this is the last thing I'm going to do here. And guess what they did? These look familiar. And what was your new column? So what's going to happen is we're going to pick it up here tomorrow, okay? We'll pick this up here tomorrow. All right, thank you.